Okay, in this video I'm going to talk about fundamental theorems for the gradient, divergence, and for the curl. So I'm going to start with the fundamental theorem for gradient. So I'm going to start my video with the fundamental theorem of gradient. So now let's say we are considering a scalar function as t is the scalar function. So now you know that infinitesimal change of this scalar function is defined as dt. So dt is equals to you have seen that I've written in terms of grad t dot product with dl, that is dl is the infinitesimal vector. So let's draw a diagram here. So we have seen we know that we can we can draw a diagram here. So this is going to be my xyz axis. So now if this t function is going from a to b, that means that t will be changed when it goes from a to b. So that means that so you can find the t as a to b. All differences will be integrated in between a and b. So now you have dt. So you know that you can write this as a to b because you can substitute dt with this equation. So you have delta grad t dot dl. Actually this would gives you tb minus ta, because you know that this gives you grad t. Grad t means you will have double x or double t over double x plus double t over double y plus double t over double c dot product is the infinitesimal displacement vector. So this infinitesimal displacement vector means you will have dx x hat dx dy y hat, likewise you will have. So with this you are going to get the double t over double x dx plus, so you will have double t over double x hat dx, likewise you will get. So when you differentiate, when you integrate with this, you will get this kind of expression for t. So actually what this means is that the line integral is depend on the points. Actually it depends on the path. So this is a really important theorem in the theorem when it comes to the gradient. So this is the fundamental theorem of gradient. So that means when you are going to calculate the line integral of a scalar function along a to b path, it depends on the path. It depends on the path that you're considering, actually, because we have taken the AB path. So these points are in the final outcome of this line integral. Okay, so but what happens if this A and B points coincides each other? So when this happens, A is equals B, this is going to be a closed path. So for a closed path, it's going to be A to B. The circle will be drawn to the integral symbol, and this is going to be grad t dot dl is going to be a 0. Okay, now we are going to get the fundamental theorem for the divergence. You will have a volume integral of divergence of V is equals to surface integral of V dot dA. So dA is the infinitesimal area vector. So this is going to be the surface integral of the vector field V, which bounded by the volume d tau, volume tau. So actually you have a diagram here. So this is going to be my volume. So this surface is closed by this volume, is bounded by this volume. So now if you take this surface as S, so this S is bounded by the volume. So now this is called the Gauss theorem, Gauss's theorem, or you can say this as the divergence theorem, because it deals with the divergence. So you can say this is a divergence theorem. Okay, now I'm going to go through with the fundamental theorem for the curls as well. So when we have a surface integral of curl of V, curl of V dot dA is equals to line integral of V dot dl. So this is actually called the Stokes theorem. So this surface integral depends on the boundary line, not the surface area that we use. So for an example, we have this surface here and this the line, boundary line here. So this is not the total surface. Actually the surface is going to be all over the volume. So but if we are going to take a boundary line, so that means that from this boundary line the S is the so S is the surface that we are going to use. So the total surface is going to be a lot more than that. So the surface is not going to be a closed path, but this boundary line is going to be a closed path. So now if we take a look at of a closed surface, like an like a balloon, this is the balloon. So this for an example, this is the balloon. So now if we take the mouth of this balloon, so now we have a closed path here, and the total surface will be S. So this is actually closed surface. So that means that the closed surface will be can be denoted as curl of V dot dA. So this is going to be 0 for a balloon. but when it comes to the general equation, so this surface is bounded by the boundary line. So this surface integral is depends only on the boundary line of the surface that we use. So but when it comes to a closed surface, when we have a closed surface, so it is going to be 0.